Okay, so let us start this new section, limiting values of functions. So we have already discussed a lot about limits of sequences of real numbers, objects that look like this, which have infinitely many terms, these ANs, and they are all real numbers. For each positive integer n, there is one real number. And we have discussed what it means for such a sequence to have limit L, say, where L is a real number. Now, if one looks carefully means if one goes back to the definition of a sequence, then in a sense, a sequence is just a function from the set of natural numbers. Well, the set of natural numbers, if you allow your index to start from 0, let that be the case so that we can discuss this. And what does this function do? It maps the input n, which is some natural number, onto the real number an. And in fact, in the actual definition of a sequence, it is defined as a function itself of this type, but the notation is slightly different from the ordinary notation of a function, and then we have discussed these things. Now we are going to do a similar thing for other types of functions. Say you have a subset x of the set of real numbers, and you have a real valued function on x, that is having x as its domain. Then we will now try to define things that look like this. Okay, and just like in defining the limit of a real sequence, whenever it exists, we used the notions of epsilon closeness and eventual epsilon closeness, which at the time of their instruction, the author also discussed that these are not standard terms. It's because the definition of the limit of a sequence is a little involved, at least when you see it for the first time. So the author took the help of these things to split it into parts which are easier to understand, and then all the things were taken together and the definition of this limit was given. So a similar thing now also we are going to do, and here we will need again epsilon closeness, but this epsilon closeness that we defined while defining limits of sequences is different from the one that we are now going to define, because now we will deal with functions and local epsilon closeness. So the section starts with these things. So let's start. The first item is this, the definition of epsilon closeness, 931. Instead of writing a formal definition, let me just give you the definition and explain it. So what are the ingredients we will need here? We will need a function. So let x be a subset of the set of real numbers, f be a real valued function defined on x. We also would need a real number okay, to which f will be epsilon close, and we also need epsilon. So let epsilon be a positive real number and L be some real number. Then we say that f is, the function itself is epsilon close to L if the functional value f of x is epsilon close to L in the sense of this epsilon closeness for all x in the domain X. Okay, so how will it look if we write it using mathematical symbols? That is, f is epsilon close to L if and only if the distance between f of x and L is less than or equal to epsilon for all x in the domain. Okay, so that is the notion of a function being epsilon close to a real number. And if you go back to the definition of epsilon closeness of a sequence, well, I think while defining Cauchy sequences and related things, we did something like that. So there also you would find one similar thing, that a sequence being epsilon close to a real number, something like that is already there. So they are actually the same once you recognize the fact that a sequence is also, after all, a function of that time. Now here, of course, there is an example to illustrate this. That is the next item. And in the example, we have the function the ordinary square function. And the thing to observe here is that if we restrict the function to the closed interval 1, 3, then this is the new function because the domain has changed. This function is epsilon close to something, and that epsilon is 5, and that something is 4, is 5 close to 4. Let's see how. So we need this, right, where you have 4 in place of L and 5 in place of epsilon, and the function is the square function for all x now belonging to this interval. So let x be any element in the interval, then x satisfies these inequalities because all the things involved here are positive real numbers, so we can take square on both sides, throughout, and have this. But then what does that imply? This type of calculations no doubt you have already come across in calculus while dealing with the epsilon delta definition of limit. In fact, that's what we are going to do here. So now we are interested in knowing the distance between f of x and 4, which is x square and 4. So we are going to subtract 4 throughout. That will give us minus 3 less than or equal to x square minus 4 less than or equal to 5. Since minus 5 is smaller than minus 3, so these inequalities further imply this. But then we already know that these inequalities are equivalent to this single inequality involving absolute value. So that's how all the f values are 5 close to 4. The distance of all of them from 4 is less than or equal to 5. So that is one function being epsilon close to some concrete L. And now next we have the definition of local epsilon closeness. This will be item 933. So the thing about epsilon closeness is that something happens for all the functional values. For all inputs in the domain, something happens. All the functional values become epsilon close to L. But local epsilon closeness, the name clearly suggests that here it's not going to be like that. Okay, it will happen only for some values, not necessarily all. So here also the starting is almost like the previous definition. We still have a subset x of R. We have a real valued function defined on x. We have an epsilon which is a positive real number, and we still have a real number L. Okay. Now we say that f is epsilon close to L. Oh, okay, where I needed to mention that, right? But that should be mentioned here before saying what local epsilon closeness means. And that is, you have another thing in your ingredient, that is a point x0, x0, which is an adherent point of the domain. Recall what an adherent point is. An adherent point of a set of real numbers is a real number such that no matter how small you choose a region around this x0, x0, there will be at least one point of x in that region. And by region, of course, I mean that open interval given by that inequality. We already know those things. Okay, so now we say that f is epsilon close to L near x0 if there exists a positive delta. So in this definition I have just now said that inequality is going to be true for only some x, more specifically for all x in some small region around x0. So to have that region we will need delta. There exists this such that the restriction of the function f to what set? To the subset of x where the points are all within a distance delta, within a distance less than delta from x0. This restriction is epsilon close to L in the sense of the previous definition. So now all the x are not, for all x in x, we do not necessarily have f of x epsilon close to L, but only for these x. Those x in x that are close to x naught in this sense, that is, they are not very far from x naught given by this delta. The distance does not go beyond delta, or even it does not reach delta. Actually, if you want, you can write less than or equal to here also. Nothing will ultimately change. But anyway, this is how the definition is given. But what is the meaning of this definition? So clearly, we have finally said what we said here in terms of the previous definition of ordinary epsilon closeness. But if we now unpack all the things and write what it actually means, then it will be this. Clearly, this is equivalent to the following. Now also the distance between f of x and L is less than or equal to, no? That's how we have defined epsilon closeness. But again I am saying, when you do analysis in definitions this type of inequalities, whether you use strict inequality or the ordinary one which has a possibility for equality, it does not really matter in the end. So this will again happen, but for all x in x, but not for all x in x, such that this is true. That's because you can understand that it's a very heavy requirement on a function to be epsilon close to some real number. All the values of the function need to be epsilon close to that real number. Instead, most of the functions will exhibit that type of behavior not throughout its domain, but maybe somewhere in a local place. So here we have one example for illustrating this. Now the function we are going to consider is that previous square function restricted on the closed interval 1, 3. Okay, instead of viewing f as, let us call the restriction itself f. Then this f is not 0.1 close to 4. say now this is our epsilon value. For that to happen, at least one value of f, that is for some input x, should not be within the distance 0.1 from 4. It should be farther than that. Since f of 1 is not 0.1 close to 4. Why? What is f of 1? F of 1 is 1 square, which is 1, and the distance of 1 from 4 is 3, and that definitely is not less than or equal to 0.1. But f is 0.1 close to 4 near to, okay, near to, so that x0 or x0 here in this case is 2, because when you restrict f to this set, such that the distance between x and 2 is less than 0.01. If you look at this restriction of f, then this is 0.1 close to 4. You can in fact verify, like the previous example, that this is the case. In fact, let's just go through the calculation for once, just to see that this actually is the case. So now our x is not simply just a real number that is greater than or equal to 1 and less than or equal to 3, but this is also true. So let us start with this and see what we get. So that means if x belongs to this set, then we have this, which implies this. So if we now add 2 throughout, what shall we get? 1.99 is less than x, and x is less than 2.01. And now if we square, okay, square all the terms because they are all positive, then you are going to get these inequalities. 3.9601 is less than x square, and squaring this 2.01 we get 4.0401, and we want to know how far x square is from 4. So we then subtract 4 from all the numbers here, and that gives us minus 0.0399 less than x square minus 4 less than 0.0401. And you can clearly see that minus 0.1 is definitely less than this. That's because if you forget the minus sign, then this is greater than this. So these inequalities imply this, and similarly this is definitely less than 0.1, and that's how we have this. So for all x in this set, the functional values which are x square satisfy this distance requirement, and that's why this statement is justified. Although the entire function is not 0.1 close to 4, but locally it is near 2. And there is another example which is about that same function. And this is another statement that same f is not this time again 0.1 close to just like it's not 0.1 close to 4, it's also not entirely 0.1 close to 9. However, locally it is, and by now you have probably guessed where. See, in order to be close to 4, in order for a square to be close to 4, the number that you are squaring needs to be close to 2. So that's why that closeness happened locally near 2. So now we need to be near 3. But f is 0.1 close to 9 near 3, since the function or the restriction, and this time we need to restrict f to a region near 3. Is the delta the same? Yes. Is 0.1 close to 9. So this one also will involve one such calculation. But there is one point though in this case. Do you see that x coming from that set that we had here in that was like this, but with 2 here, then it implies that this inequality is true. But if you consider any real number x satisfying this inequality, then that x automatically also belongs to that set. Why? Because such an x satisfies these inequalities, and because of that x already is greater than 1 and less than 3. Here, however, in this case, you will see that x being in this interval and also satisfying this inequality ultimately makes this set this half open interval. Okay, so you have to be a little careful in considering x from this set. It's not exactly like that. But anyway, it can be done, and you will see that in this region, all the f values are indeed 0.1 close to 9. And now, using these two notions of epsilon closeness and local epsilon closeness, we are going to define convergence of functions at a point or limits of functions. Let me do it there. So this is going to be definition . 9(3) 6, and the author calls it convergence of functions at a point. Although we do not really ever call it so. We do not say that a function is converging. The word converging is frequently used with sequences. Okay, but if you want, you can call it like that, although it's rare. So again, here we have almost the same things, but there is a difference. So what we now have, instead of having two sets, the set of real numbers and a subset x, this time we have three sets. The definition of a limit that we will see here of functions is going to be a little more general than the ones that we encounter in calculus. Let's see what that means. So we now have a set x which is a subset of R, and further a subset E of x, and f as usual is a function from x into R. It has x as its domain, and let now x naught be a point. Is it an adherent point of x? No, this time x naught is an adherent point of E. Okay, so every neighborhood of x naught, no matter how small, will have at least one element from E, and L is some real number, of course. Now this is how we are going to say things. We say that if, this part sounds very strange, converges to L. In other words, the function f has limit L, which is what we are more familiar with. Anyway, so f converges to L at x naught in E if for every epsilon greater than 0, f is locally epsilon close to L. If f is epsilon close to L near x naught, and you can see that here we are defining this thing in terms of the previous definition, that is in terms of local epsilon closeness. So if this happens, then we say that f converges to L at x naught in the set E, and we write a notation for that which looks like this. This part we already know, but this a little extra part is there. X must lie in E. Okay, in order to express this symbolically, we write like this. If f does not converge to any real number at x naught in E, then we say f diverges at x naught in E. In E, whether you write in E or not actually does not really matter, because this language, this way of saying this entire thing is very rarely used, not by the author himself. And in this case, when f diverges, or in other words, in more familiar terms, f does not have a limit at x naught. When that happens, then this symbol, the left hand side symbol, is kept undefined. Okay, it does not have any meaning in that case. So this is the definition of the limit of a function. Now this definition, just like the others, needs a little more elaboration. But just give me a moment, okay? It's very difficult in this extreme heat to continue, but still I have some more things to say. First, we need to say what all these things mean at once, okay, without using the previous definitions. We used those other rather artificial definitions because otherwise we may not be able to get what the idea is trying to say at once. But now that we have seen it in its entirety, so we can unpack and see what it means. So what this thing ultimately, of course, means is this. We say that this is the case if for every epsilon greater than 0, f is locally close to L, locally epsilon close to L near x naught in E, and that locally that part will be taken care of by delta. So for every epsilon greater than 0, there exists a delta greater than 0 such that this is epsilon close to L. That's what it means, right? But what does this mean in turn? It means that whenever your x belongs to E and whenever the distance between x and x naught is less than delta, then the distance between f of x and L is less than epsilon, or less than or equal to epsilon, whatever you want to use. So for every epsilon, there should be a delta determining that locality in which this thing will happen, near x naught, such that if these conditions are true, then this is also true. That's what the limit b of f being L means. Okay. Now there is a remark about this slightly unfamiliar part of this limit, this limiting value, because we do not see this definition, this notation. What we see in calculus is something like this. We are more familiar seeing this and not actually this. But this definition, which is slightly more general, has been used by Tao, and the next remark is about that aspect. The author himself says in this remark that we will sometimes suppress this E part in this notation and simply write like this. So this will be remark item number 7, I think, yes. But there you can run into problem if you carelessly do not write E ever. And let's just see one such example. You consider the function f from R into R given by this rule. F is defined to have the value 1 if x is 0, but is defined to have the value 0 if x is a non-zero real number. So that if you want, you can draw the graph of this function also. The graph is just very simple. It is so simple that it's almost invisible. So the graph is the entire x-axis except the origin, where the function has the value 1. So it's a broken line. That means the x-axis from which this single point has been taken apart and it now resides here. So that is the graph. And for this function, it really matters whether we consider E in the limit or not. The limit will change. So let us first see that this limit is equal to 0. What do we need to prove that this is the thing? You choose any epsilon greater than 0, you then need a delta greater than 0 such that whenever your x belongs to E, so what E are we choosing? The set of all real numbers from which 0 has been removed. So if your x is coming from that set and the distance between x and 0 is less than delta, then we need to show this. Now if your x is actually coming from this set, that means what? X is a non-zero real number. Okay. And say it also satisfies this delta, where we are not specifying delta for now. But let us see what happens to the conclusion of this implication. For such x, the functional values are all equal to 0. So this inequality anyway is true because epsilon is greater than 0. So it does not matter what delta you choose. You can choose any delta. For specificity, you can choose delta equal to 1. That's it. So that is why this limit exists and it is 0. However, if you now change your E and consider the entire set of real numbers, unfortunately this limit does not exist. How to prove that? Suppose the limit exists and is L, which is some real number. We of course don't know what L is, but say there is one such real number which is the limit of this function. So then all these conditions must be true for any value of epsilon. In particular, if you take epsilon equal to 1 over 3, then also all those things should be true. That means for this particular value of epsilon, there should be a positive delta such that whenever your x is a real number. This time, since E is the entire set of real numbers, so if x is a real number whose distance from 0 is less than delta, okay, then the distance between f of x and L should be less than 1 over 3. Now it does not matter what delta actually is, because we don't really know what delta will be. We just have forcefully supposed that this limit exists and it is L. So for this epsilon equal to 1 over 3, there is some delta. We don't know what it is, but there is. It follows from our supposition. So actually we are looking at this neighborhood, right? I need another such figure. We are looking at a neighborhood of 0, because that is our x0 now. Neighborhood of 0, that is the open interval minus delta comma delta. If your x is coming from this neighborhood, then the distance between f of x and L should be less than 1 over 3. And this will now create problems for us. That's because no matter what your delta is, so what I'm trying to say here is that no matter how small delta is, and as a result no matter how small this neighborhood is, you will always find some x in this neighborhood that is a non-zero real number. Delta can be very close to 0, but it cannot be equal to 0, right? It is greater than 0, so you can always find a non-zero real number x in this neighborhood. For that x, also this should be true. But for that x, what is the f value? F value is 0. So that means you are getting what? This. However, lying in your neighborhood is the point 0 also. Okay, and this also will be there in the neighborhood regardless of what delta is. And this should also be true as a result. But what is this? F of 0 is 1. Okay, so we now have two inequalities like this. Now watch this. 1 is equal to its own absolute value because it's positive, and that can be written like this. And here you can use the triangle inequality. And using these two inequalities, both of them are less than 1 over 3. So you get the absurd conclusion that 1 is less than or equal to 2 over 3. It's false. So that means our supposition must be wrong, and that's why this limit does not exist. Now all these things may seem very peculiar because we are not really familiar with this slightly more general version of limit of a function. What we learn in calculus instead is this. In calculus, when we write a statement like this, say, let me give you a concrete limit. You are probably familiar with this limit. And in this notation, it's the notation itself is such that it's understood that x is not equal to 0. In other words, if we go back to our notation, this notation assumes what? It assumes that x naught is an adherent point of E. What does that mean? It means that x naught may belong to E. Okay, this may happen. Or x naught may not belong to E. So what we normally use in calculus is this case, and because x naught then has to be an adherent point, in this case x naught is a limit point of E. For example, in that limit from calculus, the function that we have here, sin x over x, this is defined on the set of all non-zero real numbers. So your E here is this set, and 0 does not belong to E, but 0 is a limit point of E. Okay, and hence an adherent point also. So this is the case we are more familiar with, but the author has allowed a slight generality, because of which some such peculiarities will arise. But this hasn't been done for nothing. By allowing our limit to be slightly general, the author must have something in mind. Okay. So you need to understand, you forget about previous definition and the definition now. You just need to understand what the definition says. Without going into the technical details, it just roughly says this: f of x will be close to L if x is close to x naught and x is in E. That's it. And the only condition that you have to remember is this: if you do not assume x naught to be an adherent point of E, then something goes wrong with the definition. The definition becomes, it doesn't become meaningless, but it becomes useless. We will discuss about it more in the subsequent videos on analysis. Okay, so let me just end this discussion with this remark itself. After this, there is a result which we will prove in the exercises. That result basically tells us that in order to find such a limit, it's enough to consider sequences. And let me just end with this statement that in a metric space, I am uttering the word metric space, okay, well in advance, because we are still far away from metric spaces, but we will get to them, okay, at one point. You already know that the set of real numbers is a metric space with the usual metric given by the absolute value function. In a metric space, the topology of the space is captured entirely by sequences. That's why nearly everything that you see that is defined in a metric space has, in one way or another, a sequential version, which makes life easy. But that is unfortunately or fortunately, depending on how you want to look at it, not the case in general topological spaces. Okay, anyway, more on these things later. So that's just it for tonight. Our next upload is this coming Tuesday, and on Tuesday let's go back to calculus. So see you on Tuesday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.